Hello. I hope I am audible. Let's start the live session 4 for the chemical crystallography course. I'm Shani Verman, the PMRF TA scholar. Currently, I am doing PhD in the Department of Chemistry, IIT Hyderabad. In today's lecture, we'll be covering a few problems regarding the week 3 and week 4. In week 4, we have learned Miller indices of crystallographic directions and planes. How to detect Miller indices, what are indices, and how we can denote them in a in a lattice plane or at a certain direction. We learned to calculate the planar and linear densities. Then we have seen how to detect the packing factors and atomic factors. Then we have learned few ceramic structures like perovskite, NaCl, rocks or rock salt CSCl, and ZNS structures and all. Then a brief of X-ray diffraction, how X-ray diffracts. We have learned about that, the Black's law most importantly. Now we'll be solving a few previous year problems. So this one from the week 3 quiz. So okay, this question this question states that which presentation this presentation relates to which of this space groups. So first we'll be deriving all of them. But before starting derivation, we can just look into the structure and we can say, let's say, one sec. So this is the first point, and we can see there is some inversion happening here, right? The plus sign becoming the minus. So some inversion is going on, right? And we are also seeing, let's say this is the number 2 point. And in the number 3 point, we can say that there is some plus up translation along this direction, right? So we can say that we have to say that must be some glide plane here. Glide means a mirror image or a reflection plus half translation. So there must be some glide plane associated. And here we can see from the option, this is the option where a glide plane is associated. So this must be the option, but we'll derive it slowly. We'll go through the options one by one. Yes, Gautam, you can get the videos of those sessions. Just like you must be getting some notifications regarding these live sessions. You can join in future. You can join through those Google links, and otherwise you can also go to okay. Go to the chemical crystallography NPTEL page and where videos of this each weeks are uploaded. You can scroll down and you will be getting like download videos option. At the end of this session, I'll show you the demo, like how to get these videos. And on the download option, you can get all the live sessions of 1, 2, 3. I have done 3 live sessions till now. You'll be getting all of them. Okay, so now coming back to the question. So the first one space group is P2 by M. So P2 by M means P2 by M. So we'll draw a rectangular lattice first. So this is our first point. I'll draw all the translation related objects. Yeah, these are 4 points. And two means a twofold rotation along the z-axis. Z-axis means like this is y and this is x. Then z is the perpendicular to the plane of projection. So upon twofold rotation, it will go here. So this is if this is number 1 point, this is number 2 points. Now the slash aim means the mirror is perpendicular, right? Okay, let's turn this around. Let's say the twofold is like along the y-axis, then we can say these are the aim planes, the mirror planes. The mirror planes are perpendicular to y or along z. So it will be easier for us also. Then according to the mirror plane, we'll get the reflected images like this, right? So one, two, three, four, three, four. There are four objects will be here. Similarly, I'll draw here also. Mm, mirror planes like this. So here also, here also, here also, here also, you'll be getting those points. So now we can see there are four equivalent points for P2 by M, right? Let's say I can write as well. See if this is X, Y, Z, then twofold parallel to Y means X bar, Y, Z bar. Then on this, if we operate a mirror perpendicular to Y, then X, Y bar, Z. Now again, if we apply this to two-fold rotation, it will be X bar, Y bar, Z bar. And similarly, this is this. You can see this is inversion related and this is also inversion related. So there are four equivalent points. The next one is P21. 21 means screw. Screw means rotation plus translation. So we'll do this. And for screw, we draw the axis as half arrow, not full arrow, not like this, but this. Okay. So now I'll just draw the translation related objects. Now, 2-1 screw means uh, twofold rotation plus half translation along y. So this is the y-axis. So twofold rotation, it will come here plus half translation, it will go there. So we'll just remove this one because this is the intermediate state. Now this is the point. Now similarly, here also you'll get one point. So this is one number point, this is number 2 point. So you can say if it is x, y, z, then 2-1 screw parallel to y, you'll get x bar, y plus half, z bar, right? Because this is, see, if it is two parallel to y, you are getting x bar, y, z bar. Similarly, x bar, y, z bar. And due to these 2-1 screw means half translation along y axis, you are getting a plus half extra. So z equals to 2. There are two equivalent points. Next one is PC. PC means just a primitive lattice with a C glide. Okay, so this is primitive lattice with a C glide. Let's say the C glide is along Z direction. So we have to erase this because we know C glide we draw as dashed, not as solid lines. So this is a C glide. This is Y means Y axis. This is C glide or C means it's in Z direction. So PC, if we apply, so let me draw the points first. Okay. These are the points. Now, if we apply C glide, it will C glide means what? Mirror plus half translation, right? So mirror, this will be the mirror and half translation. Let's say this. So this is the intermediate point. We'll erase this. Now you'll be getting a similar point here also. So there are only two type of points. So the first point, if it is x, y, z, then C glide parallel to z, or you can say C glide from the picture only. You can say C glide perpendicular to y because y and z are two perpendicular axes. So it will be on half translation along z axis, right? So x bar, y plus y and z plus half. Not x bar, this will be x y bar. Let's okay. So C perpendicular to y means y should be like y will get inversed. Right. So y a bar will come upon y. X is as it is, and since the half translation is along z, so z along z axis you will be getting z plus half. So the coordinate of the C glide point will be x y bar z plus half. And for this also, for P21 by C also, will be generating points. Like from here only, you can say this, let's say, so X, Y, Z, C perpendicular to Y. First we'll apply P21 to 1 perpendicular to Y, parallel to Y. So you will get X, X bar, Y plus half Z bar. Right. Now along this I'll apply C glide perpendicular to Y. C glide perpendicular to Y and the half translation along Z axis. So we'll be getting X Y bar Z plus half. Now if I apply 2 1 screw again on this, you'll be getting X, okay, 2 1 perpendicular to Y means along Z it will be perpendicular, right? So X Y plus half bar and Z plus half. It's a bar here. Now, C21 perpendicular parallel to Y means 21 also perpendicular to Z. That's why we are getting a bar here. Okay. And here, this is also, you can say, this is also related as C glide perpendicular to Y. And that's why C glide perpendicular to Y or C glide parallel to Z means half translation along Z. That's why you are getting a Z plus half and bar as it is. And then on Y plus half, since it is C glide is perpendicular to Y, you are getting a bar here. So these are the equivalent points. Z equals to 4. Yeah. So this is the first question. And the second question is MMM crystallographic point group is equivalent to D2D molecular point groups. Now MMM, we have to draw. See, in MMM, we have to first see like this. If this is the point, then okay, I'll just draw like that. If this is the point, then let's say the mirror plane is here, then you'll be getting a point here. Now there is another perpendicular mirror, right? So you'll be getting a mirror, let's say here. Then this is the point. This is the point, right? Now let's say, yeah, this is a MMM. Now you can say if there is a mirror point here, yeah, okay, I'll just draw. If there is a mirror like here, we'll be getting another point, and similarly, another mirror point will get generated. Like this. This is MMM. Now D2D molecular point group. This is crystallographic point group, right? And D2D means diagonal one. So will be the symmetry elements? There is a C. Okay, right first. D2D means there is one C2 and there are C2s perpendicular to this C2. Okay. And there is a sigma D plane. So we can take one example. We can take as aline. Aline is what? C double one C H H. These are in plane, and this is above and below the plane. So if this is C2, then there is also C2. So this is you can say see, if this is C2, there are mirror planes generating, and if this is we are considering, then also mirror planes are generating, right? And sigma D plane is what? The sigma V plane just perpendicular to the principal axis, right? And also, sorry, this will be the principal axis, and also there are perpendicular C2 axis. Like if C2 axis are perpendicular to sigma V, it is called a sigma V, right? So these are the case. So you can say there are also mirror planes generating. You can say this is a mirror plane, this is a mirror plane also. C2s are nothing but the mirror planes. So whether MMM crystallographic point group is equivalent to T to T molecular point group or not, actually there are two molecule MM generating, right? Not three. So this will be false. Please, false, false. Now, the second one. So, CC, PC, PM, P4, MM are chiral space groups or not. Now, from the space group chart, we know that there are two types of space group. Firstly, we divide as centrosymmetric and non-centrosymmetric. Non-centrosymmetric means there is no inversion center, and centrosymmetric means there are inversion centers. Now, non-centrosymmetric space groups are divided into two sets, that is chiral and achiral. Chiral are what? Where mirror planes or glide planes are present. Glide planes are present. And achirals are what? No mirror or glide planes. Now, from the options, this is a C-centered lattice, but there is one C. This is C glide. Here also it's C glide. Here also it is PM mirror. P for MM. These are also mirror. So these are chiral space groups, not achiral. But yeah, these are chiral space groups. So it is true. Okay, let me check once. Yes, sir. Okay, I have done one mistake. This is achiral, where M or mirror glide planes are present, and chirals are there are no mirror glide planes. Yes, because chiral, like if four ligands are there, they are not equal. So no mirror planes or glide planes, no mirror planes can be generated. So these are chiral, but here it is called. So these are all achiral point space groups. So this one is false. This because these are all achiral. Now the next one is 6 mm, 6 mm crystallographic point groups. 6 mm we can draw like this. That's the first draw like this one. 6-4 symmetry is there. Then let's say 6-4 symmetry is there, means it will go here, 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 and also a mirror plane. Right. So a mirror plane is there, here, 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 and here. And also, if we generate a mirror plane, we can generate a mirror plane like this. It will be the same. Say this are and this are same. These are same. So mirror planes are getting generated. Like this is M, and this is sixfold mirror. Sixfold axis is perpendicular to the projection of the plane projection with the plane where we are drawing. So this is 6 mm. 6 mm. Now C6V molecular point group. C6V means there is one principal axis C6 and one sigma V means a mirror plane is perpendicular to the C6 principal axis. So let's take one example. Um, there must be something hexagonal, right? Or you can just, yeah, any, no, this will be big too big then. This it's big. Okay, let's take like this. Okay, I found one example where it's saying C6 AME6. In eta 6 the hapticity. Then it is like this only. Okay. Of course, these are in inches. H's are there. So this is the six-fold rotation axis is here. Six-fold rotation axis is here, and there are C2 axis and C3 axis are also here. C2, C3 are also here. So, if we can relate the 6 mm crystallographic point group to C6V molecular point group, we can say that yes, there are mirror planes. Like this can be a mirror plane, like this principal axis only. Uh, then there can be mirror planes like this and this. Okay. So yeah, this is equivalent to 6 mm crystallographic point group is equivalent to C6V molecular point group. Then the next one is P2, P1 bar, Pn space groups has Z value equals to 2. This is true or false. Now P2, it will be just P2 is just a two-fold rotation. No? If this is the point, then there will be a two-fold rotation. Mm, Now this is the two-fold rotation. So there are one and two equivalent points. Here you can just write it 2 parallel to y-axis. It will be x bar y z bar z equals to 2. Now the second one is p1 bar, just one inversion. If this is the point, so there is your inversion, right? So it will be x y z. Inversion means it will be all will be inverted, right? Now the next one is PM. PM mirror planes are like this. So if this is the mm, mm, point, then this will be the point. Now there will be another points here also. So x, y, z mirror is along z axis means perpendicular to y. It's x, y bar, z. So all has z equals to 2. True. The answer is true. Now our equivalent points are C2 space group. Yeah, from C, by seeing only you can say that this is true because C the lattice type is C centered. It's C, right? So there must be one. If there is one point, it's X, Y, Z, right? For primitive lattice, this is the only point. But for C centered lattice, there is one point here also, and it is denoted as X plus half, Y plus half, Z. Let's say this is the x direction, this is the y direction, is half, half along x, half along y also. So this is the x plus y by y plus half z. Now if you apply C2, C2 means twofold rotation, right? Twofold rotation along y axis. So it will be x bar, y, z bar, and here also twofold rotation along y axis. It will be x plus half bar y plus half z bar. You can also write it as minus x minus 2 y plus half z bar, or like minus x minus 2. Minus 2 means the point is out of the unit cells. So to include the point inside the unit cell, you have to just add 2, like plus 1. So it will be x bar minus x, we can write it as x bar. Then x minus half plus 1 means plus half y plus half z. So basically, this is 1 point, this is number 2 point, this is 3 point. Here it will be 3, and here it will be this. So yeah, 3, and this is the number 4 point. 1, 2, 3, 4. So these are the 4 points, and this one is this one, this one is this one. So yeah, these are equivalent points of C2 space group. The next one is from the week 4 I have taken. So the first question in the lectures only sort of is asked to determine the linear indices of the directions between the following planes. We'll just draw one lattice, just one big lattice. So let's say this is our origin. Okay. Then then okay. Then half 1 0 means half along x axis. So this is x, this is y, this is z axis. So half along x axis, 1 unit along y axis, and there is nothing along z axis. So this is the first point, half 1 0. Now to 0 0 1. This is 0 0, only in z direction it's 1. It is 0 0 1. So this will be the direction. So this is the first direction. Now the second one is from 0 0 0 here only to 1 1 1. 111 means 111 means 1 up to here, 1 up to here, 1 up to here. So this is 111, right? From 000 to 111. So the second one. So this is what? This is just a body diagonal. Then the next one is 1 from 100. This is 100 to 010. 010 is here. 010. So this is what? This is a phase diagonal. And this is an right here. Body diagonal. This is phase diagonal. Now the next one is 1 half 1. 1 half. Now 1 along the z axis. So this is the point. 1 half 1. And from half, half, half. Let's say half is this is the body center. Body center. So from here to here it is. Now, okay, I'll just write. This is 1, this is 2, this is 3, and this is 4. I've already told. This is 3. And now I'll draw the 5, the fifth number. From 111, sorry, from 111 to 0 half 0. In 0 half 0 here, let's say here, 0 half 0. So it is this. This is number 5. I'll just draw. This is number 1. 1, 2, 3, 4, 5. Yeah, fine. So this will be the answer. And the next one is determine the planar densities of the face-centered cubic lattices for these planes 100, 110, 111. Okay, so let's draw a big one first. Yeah. So 100 plane is what? Means the intercepts are along y and z axis are infinity. Means the plane is must be parallel to y and z axis, but along x axis it is 1. So this is the plane, first plane, this plane. So this is the 100 plane, okay? 100 plane. Now it is his centered cubic lattice. Okay, we'll just first put 8 atoms in the 8 corners. Then on each face center, we'll be drawing one. Six, 1, 2, 3, 4, 5, 6. Yeah, six face centers. Six face center points. Now here. Now for 100 plane, how it If we draw just the plane, it is this. Just draw them. So this is this plane, right? And along the plane, how it shows, there are four atoms in the four corners and one center at one center. And this is the body diagonal, face diagonal, right? The face diagonal. So this is the face diagonal, and face diagonal. What's like how the face diagonal forms? Like so, this, this. This is the face diagonal. This much only. So if the radius of each atoms are r, then the center one is taking the diameter equals to 4r. Now, the length of the unit set, let's say it's A0. So, A0 for face-centered cubic lattice, A0 equals to 4R. And A0, A0 equals to 4R. The diagonal of any square is root 2 A0. Then root 2 A0 equals to 4R. Then R equals to root 2 A0 by 4. So for face-centered cubic lattice, 100 plane seems like this. Now the surface area would be the uh, of the lattice. It is A0 square because this is the surface, no? And the length of each edge is A0 only. So it's A0 square. Now area covered by the atoms is, see, this is a square, right? Now in this square, this much amount is what? 90 degree. 90 degree means is how much of 360 degree? It's one fourth, right? So there are four, and for each circle, the square, the area is pi r square. So there are four 1 by 4 pi r square, right? So this circle's area is 1 by 4 pi r square. And how many are there? 4. So we are writing it as 4 into 1 by 4 pi r square. Now for this circle, it's pi r square only. So plus pi r square. So the total area covered by the atoms will be 2 pi r square. Then the planar density will be area covered by the atoms divided by the surface area, right? So 2 pi r square divided by a0 square. Now r equals to root 2a by 4. Root 2a by 4 means 2 by 4 square, a0 square by a0 square. We'll cut this. Now it will cut 1. So it is pi by 4. Now you can just calculate the number. Now for 1, 1, 1, 1, 1, 0 plane. Now along z-axis, it will be parallel, right? Otherwise, it is the intercept is 1 only. So 1, 1, 0 plane. So this will be, see, this is one intercept, this is one intercept. If we take this this plane, then it will be again like parallel to y-axis also. So y would be also not one intercept, right? So this is not the plane. This is not the plane. So the plane is actually this one. I'll take another color. See, one along x-axis also one, along y-axis also one, and it is parallel to z-axis. So this plane So this plane is 110. Now, for 110, how will the surface look? This is, let's say, this is 1 0 at C. At four corners, there are four atoms. Now, uh, along the edges, along the two edges, there are other atoms also. So it will be like this. Okay, it will be like this also. So now, similarly, what will be the surface area? And write it is a surface area is, and this is the body diagonal. So this is root 2a, and this is this much is a0 only, right? So the surface area is root 2 a0 into a0 equals to root 2 a0 square, and area by atoms is how many? Like 1 by 4 pi r square are there? 1, 2, 3, 4. So 4 into 1 by 4 pi r square, right? And how many there are? These are two semicircles also. 2 into 1 by 2 pi r square, right? So again it will be 2 pi r square. Okay. So again it will be 2 pi r square. So with that, planar density will be 2 pi r square by root 2 a0 square. Now it will be root 2 pi r means what? Root 2 a0 by 4 square divided by a0 square. A0 square will nullify. Then we'll get root 2 pi into 2 divided by 4 square. Right. So 2 root 2 pi 4 into 4 this will be 2. This will be 2. So pi by 4 root 2. Now the next one is 111 plane. So this will be like uh, so the 111 plane would be this, like one here also, and one here also. Since this is the origin. So, and this is the origin. So the plane would be like this. So you can see this lines, these edges are also phase diagonals. These are also phase diagonals, right? So this the surface looks like a triangle, and in triangle, how many 60-degree angle are there, right? And here also a semicircle will be there. Here also a semicircle will be there. Here also semicircle will be there. Hence, area covered by atoms will be 3 into 1 by 6 pi r square plus 3 into half pi r square. 1 by 2 plus 3 by 2 pi r square plus 2 pi r square. And area, surface area, what will be surface area? Surface area of a triangle is root 3 by 4, right? root 3 by 4, since this is root 2a0, root 2a0 square. So it is root 3 by 2a0 square. Hence, planar density would be 2 pi r square divided by root 3 by 2 a0 square. Now this will be 4 pi r means root 2 a0 by 4 square divided by root 2 a0 square. A0 square will be nullified. 4 will be nullified. So it will be 2 pi divided by root 3 will be intact, and there will come a 4 root 3. Now 2 will be here, pi by 2 root 3 will be the answer. Okay. So this is the planar densities of these three faces for face-centered cubic lattice. Then the next one is sir has asked us to detect the structure of the perovskite. Now perovskite is one of the ceramic type structure. Now here I have included two like a few examples like MTiO3 where M is barium or calcium, and then there is NaNO3 where M can be tantalum or niobium. So let's detect the perovskite structure first. Now perovskite structure has structure type of ABX3 where A atom, here it is A atom, there is B atom, and here it is oxygen. It's 2 minus. Mostly it's AbO3 only. So B atom is mostly found in 4 plus state. Let's say I'm taking for Ca2 plus, Ti4 plus, oxygen 2 minus. Right. So this one is the larger cation, this one is the smaller cation, and anion binds with both the cations. Okay, so I'll be drawing the lattice structure now. So the larger atom will be sitting. So the larger atom, let's say like this, and draw this. So the larger atom will be sitting in the center of the lattice, and then the smaller cations, let's say it's this, the blue. Okay. So it will be at on the face centers, like no, sorry, edge centers. There are how many edges? There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12 edge centers. So there are 12 Ti4 plus cations. And the anions will stay where? Anions will be staying here only at the corners, at the 8 corners, right? So this is the structure. Okay. Now we can detect the formula like the unit cell the formula unit or the number of atoms into one unit cell. So for Ca2 plus it would be the Z would be just at the center, so it is 1. So for Ti4 plus it is at the edge centers. How many edges are there? 12 edges, and the edges are shared by how many lattices? So there are 4 lattices, right? So if I consider this one, so it will be considered, it will be shared by 2 lattices up up of this green lattice, one in right, one in left side, one in right side, and also one like two lattice below this point. Like the one is already drawn, the green one, and one other one is here, the right lower. So it will be shared with four lattices. So the Z will be three, and the oxygen how many? So you all know that the corner atoms are shared with the eight lattices, and it is one eighth of it. So it is 8 into 1 by 8 equals to 1. So these are the Z values of the formula units. Now, what will be the coordination of this larger atom? Ca2 plus. It's already written here that Cn cation, like the coordination number of the cation is 12 for A. A means this one, and 6 for P means for this one's. Right. So let's say how it can be 12 or 6. So for this A atom or the Ca2 plus atom here will be drawing. So there are like how many anions are nearby. So see here how many anions are nearby. So the red ones are the anion, right? So this one, or we can draw here also. Let's say if it is Ca2 plus, then this one, since it is middle, let's say this one we have drawn, then this one, it is this oxygen, oxygen. Then again the below also there are two oxygen, oxygen, this two. And now from this face, from the behind face, there are four oxygen, oxygen. Let's draw here oxygen, oxygen. So here are four. Now this comes as eight, right? Now, but this oxygen is 12. So what is the like how it's coming? It's coming as here oxygen, oxygen. So what happens is these oxygens are coming from the other lattices. So yeah. So this will be the point for Ca2 plus. Then for Ti, so Ca you can write it as CaO12, right? 12 coordination number. Now for the sixth one, the B atom, that is the titanium one, it is drawn in blue. Yeah. So it is actually connected with, let's take one example. Let's say this one. Okay. This you can see this one, two, three, four, five, and here also from the next one it will come as here also it will come one oxygen. So this will be the six. So TiO6. The coordination number is 6. And this is called octahedral, and this is 12. Coordination is dodecahedral. And now the coordination number of the anion. Coordination number of the anion means the for this one. Let's take for this one only. Okay. So for this one, it will be, see if it is this, then I have already told you that this can be shared with four lattices. So there can be four, okay, four Ca2 plus already. Okay. Ca2 plus at the center, this one's. If we write it as here, Ca. Now, how many titaniums are possible? See, this one, so one is this one, and another one will be the above one, right? Mm, This is the titanium test. So this is octahedral. Now this is a perovskite structure, and you can see. So the next one is the Miller indices of the above diagonal. In this is Miller indices. Okay. So this diagonal is, see, if this is 0, 0, 0, then this will be here. It's come along is, let's say, if it is, okay, if it is here, it's coming along one at x, one along y, and one along z. So it is 1, 1, 1 to 1, 1, 1. The origin point of 0, 0, 0 can be defined anywhere in the crystal lattice. Yes, it's true. It has already been shown in the lectures. And the next one is in a cubic system. This includes this Miller indices. Yes, it's true because this is the equivalent plane. It can indicate in any like permutation combination. Okay. So the next one is the Tamil instance for a plane with intercept 3 infinity 2. With intercept, these are intercepts 3 infinity 2. Then the inverse of intercepts are called Miller indices. If we inverse this 1 by infinity 1 by 2, so it will be 3, 1 by 3. In 1 by infinity equals to 0, 1 by 2. Now if we just take this as integers, it will be 203. 203 is the Miller indices. Yeah, 203 Miller indices. Yes, right. The Miller indices of the following plane is, okay, if this is the 0, 0, 0, then x-intercept is 1, y-intercept, okay, I'll just write it here. Intercept is y, z, 1. Here y-intercept is half, z-intercept is 1 by 3. All are in positive directions, right? So inverse of intercept 1 by 1, 1 by 2, 1 by 1 by 3, 3. And now how we write Miller indices? Indices, it is in first bracket, right? So 1, 2, 3. Next one is the plane representing the Miller indices 1, 1, 0. Okay, 1, 1, 0 we have already seen, but still I'll do. See, this plane is, for the first one, this plane is parallel to what y-axis and z-axis. In 110, if this is the Miller index, means if we inverse it, the intercept will come as this, means this plane is parallel to z-axis. Okay, this plane is also parallel to z-axis, but also parallel to y-axis, so this will not be the option. Now this plane, the second one, this one, this one is parallel to both x and z axis. So this will not be the option. Now the third one, this plane is not parallel to x axis, not parallel to y axis. Okay, just a sec. This plane is so for this plane is not parallel to any axis, right? But z axis it's parallel. So if we do the math, so it will be 1, then 1, and this is parallel to z axis. So this is possible, right? Now if we do this, okay, I have done mistake here. That's fine. So it's not intersecting with x-axis only. It is not intercepting. There is no intercept on x-axis, right? So it is just z-axis parallel. So this will not be the option. So the next one is, let's see if this is the origin. It's intercepting x-axis here. So this plane would be 0. This plane is 0, 1, 0. And this one would be a 1. This much is also 1, 1, 1. And there is it is parallel to z axis. So this is 1, 1, 0. Yeah, fine. So this is the answer. So the next one is planar density of 110 plane in BCC lattice. So for BCC lattice, so at 8 corners, then one at center. Okay. Now one center, how this comes? This comes as body diagonal, right? So I'll just draw like this. This is the body diagonal, let's say. And for body diagonal, give the body diagonal is root 3, 1. This is root 3 A0. If A0 is each edge, if this is A0, this is root 3 A0, the body diagonal, and it will be equals to R plus 2R plus R. R of this, 2R of this, and R of this. It is 4R. Then R equals to root 3 by 4 A0. Now for 110 plane, just now we saw this is the 110 plane. So if this is the plane here, right? So if this is the plane, it contains the body diagram. Mhm. So what will happen? So the surface will look like this with 4 corners and one at center. So the surface area would be, how much is this? This is root 3 A0, right? So root 3 A0 into sorry, this is not root 3, this is phase diagonal. So this would be root 2 A0, root 2 A0. So this one is root 2 A0, means root 2 A0 square. Then area covered atoms by the atoms would be 4 into 1 by 4 pi r square for this 4, and 1 pi r square for this interval. So this is 2 pi r square. Then the planar density would be area covered by the atoms divided by the surface area, root 2 A0 square. Means it is already root 2 pi. R means root 3 by 4 A0 square divided by A0 square. A0 square will get nullified. And then this would be root 2 pi into 3 by 4 into 4. So this would be 3 pi 8 root 2. Right? Yeah. So 8 root 2. This would be the answer. 3 pi by 8 root 2. This one. The planar density for 200 in FCC lattice. Okay. For FCC lattice, this is the FCC lattice, and for FCC lattice, what happens? Like this, what happens? The phase diagonal becomes equals to the 4R, right? 4R equals to root 2 A0. Then R equals to root 2 by 4 A0. This happens. Now, for 200 plane, if this is 000, then 200 plane means, see, the 200 plane is, if we inverse this, it will be 1/2 half. Means the intercept will be this. So half along x-axis, this is x-axis, half along x-axis, and infinite means there are, this is perpendicular to y and z axis, right? This will be the thing, half 0, half along x, but there is no y intercept. Y is perpendicular, z is perpendicular, y is also perpendicular. No, the half along, no, sorry. Okay, so basically the plane would be this, right? And for this plane, the face would be here one, here this. Okay, there I have done some mistake. So then, see. So the face centers here one, here one. So 200 plane will be half along x here and parallel to x, y and z. So this should be this, right? Here, this one will be the correct answer. So this is the plane at the middle. Okay. So this is the half zero zero plane, half zero zero 200 plane. Now in 200 plane, if we draw the face, it will look like there is nothing in this corner, nothing in this corner, nothing in this corner, nothing in this corner. But it's doing like this. So basically the face is not containing any atoms, right? So we can't do properly. So the planet density, since there is no atom, so it will be similar to the A0 square. So it will be 0. Density to 0. Now the for MO K alpha radiation, if a data is collected to 50 degree into theta, what will be the resolution in 1 Armstrong? Now we know from the Bragg's law it is in lambda equals to 2d sine theta. Now 2 theta equals to 50 degree, theta equals to 25 degree. For molybdenum, the lambda is 0.7107, right? 0.707 Armstrong. So let's say n equals to 1 as a maximum value. So lambda 0.7107 equals to 2d. We have to detect the d only, sine 25 degree. D equals to 0.7107 divided by 2 sine 25 degree. Now this value will come at 1.183 Armstrong. Now resolution is the inversion of the interplanar distance DHKL. So it is just inversion 1.183. So it goes to 0.84 Armstrong. So this will be the answer. Now the next one is the Miller indices for this plane is okay. So this plane, so for this plane, if we are taking this as O as 000, then it will be a bit difficult. So we have to shift the origin. Let's take this is 000. Okay. So the x-intercept is x, y, z intercept. X-intercept is x-axis is along this. So it is in negative direction minus half. Y-axis in this direction, but here it is coming here. So this is, if it is 1 by 3, then this portion would be 2 by 3. But minus, since it is negative in y direction, then along z direction also it is z direction normally it is right here. So, but here it is being downside. So it will be minus. Now this much is 3 by 4. So this much will be 1 by 4. 1 by 4. Then the inverse of this will be minus 2 minus 3 by 2 minus 4. Miller indices would be, if you make it integer, minus 4 minus 3 minus 8, or 4 bar 3 bar 8 bar. So this one will be answer. The next one is HKL in second bracket represents a family of equivalent planes. Yes, second bracket means equivalent planes. What is the planar density of a 111 plane in BCC unit cell? Planar density of BCC unit cell. Okay, so it would be like this. It is 0, 0, 0. This one is the origin. Then 1 along this one, along this one. So this is the plane. And here are the corners, 8 corners. And a central atom, right? But for this 111 plane, this is 111 plane. So for this 111 plane, the center atom is not coming like within the plane, rather it's coming downward, right? So we will not be considering it. So the face will look like this for 111 BCC plane. So this is triangle. There are 3 atoms, this one, and this one. Now, you know, these are the like phase diagonals, and for this is for here, it will be okay. So, area covered by atoms. These are, you know, already 1/6. So, 3 into 1/6 pi r square. It will be 1 by 2 pi r square, and surface area, since these are phase diagonals, this lines, it will be root 2 a0. So the formula is root 3 by 4 root 2 a0 square equals to root 3 by 2 a0 square. Then the planar density would be pi r square by 2 divided by root 3 a0 square by 2. This will cancel. Now pi by root 3 r for BCC lattice is 4r equals to root 3 a0, or r equals to root 3 by 4 a0, right? So it will be a square will cancel out. It will be root 3 by 4 whole square. So root 3 will also cancel out, but this will come another root 3 back in all the 16. Okay, so this value is 0.34. So this is the answer. What is the coordination number of BCC lattice? This is for BCC lattice. See, this is the center atom, no? So it is 8. What is the atomic packing fraction for BCC lattice? So for atomic fraction, we need to show the like how much atoms is occupied um, per unit cell, right? And how much atom is the volume of the atoms. Now for VCC unit cell, you already know that 4r equals to root 3 a0, or r equals to root 3 by 4 a0. Now in there, how many unit cell are there? At 8 corners, and this contribution is 8 into 1 by 8 plus 1 at the center equals to 2. This is the Z value, right? The unit cell per atoms per unit cell. Atoms per unit cell. Now packing fraction would be volume of atoms by total volume. Volume of atoms means number of atoms plus number of atoms into volume of each atom, right? Now, volume of each atom, this is circle is only so you know that means for a sphere, the volume is 4 by 3 pi r cube, right? And how many atoms are there? 2. So 2 into 4 by 3 pi r cube divided by total volume is A0's cube of the lattice of the cube, right? And R equals to root 3 by 4 A cube, A0. So this would be 8 by 3 A0 cube, and A0 cube will be cancelled out into root 3 by 4 cube. Now here 4 4 will cancel out, 3 3 will cancel out. So it will be 2 pi into root 3 divided by 4 square. So it will come as 8 root 3 pi by 8. Root 3 pi by 8, how much it is? 0.68. Here only we got the 0.34. So the double of it is 0.68. 0.68. The two types of Zeton structure are wurtzite and zinc plate. So do you know the difference between wurtzite and zinc plate? Okay. So in zinc blend, actually, the anion packing is FCC, the closed packing, and for woodsite, it is HCP, hexagonal closed packing. So the answer will be like this, but I'll also show the structures. Is the first zinc blend. It is, so if it is a, what is, right? Then the anions will be the 8 corners and the face centers. So it's a anion up here. Okay. And then the cations. Cations are where? Cations are the opposite tetrahedral holes. I hope you know the how the tetrahedral holes are generated. So the opposite tetrahedral holes here, and then here and here. Means it is like this. Okay. I'll just remove those. So this is the structure. So if I just go in the details, so it will look like if this is the tetrahedral structure, the tetrahedral holes since so the this is a cation. Let's say this is there sits Zn2 plus, and then there will be another Okay, I'll just draw. Let's say if this is Zn2 plus, then at the four corners, there will be S2 minus, S2 minus, S2 minus, S2 minus, and the S2 minus will form this type of tetrahedron. Okay, this is this, this. Okay, then for S2 minus also, it is, if there is, let's say if this is S2 minus is here, then Zn2 plus will sit like this. Zn2 plus. Okay, I'll just draw as circle here also, here also, here also. You can see this is becoming a tetragonal tetrahedron. Okay. Similarly, for this is I'll write this is for zinc blend. Okay, for zinc blend. Now, for wordite also, the structures of each are the same. Like both Zn and S sits at tetrahedral in tetrahedral geometry only. For both of them, or for both the cases, woodside and zinc blende, the cation and anion of for both the coordination numbers are four only. But the structure is a bit different for woodside. It actually is. See, if this is the structure, then the cations means I have drawn in black. Okay. Then the cations are here. Zinc is here at the 12 corners, and then the anions are here. Okay. So like this, but the coordination and number will be the same. This is word side. So the answer I have already given here, and the true answer will be the arrangement of sulfur atoms in HCP for woodside and FCC for zinc lead. Okay. So this is up to the week 4. Now week 4 assignment is given already, and the assignment submission deadline is on 23rd of August. I hope all of you will submit the assignment. Okay. Thank you.